Dee German.
Thank you, Joe. When we were working with the Shroud, I noticed something, as Rex mentioned last night, that many others have seen, and that is the apparent increase in contrast between the image area and the surrounding cloth as one backs away from the cloth. In this presentation, I'll propose a hypothesis for this effect and present the results of some experiments I did to determine if it was valid. The basis of the inquiry is this observation I mentioned. My hypothesis is that an explanation may be that the degraded image area fibers, which have lost the shininess of the pristine fibers, diffusely scatters in all directions light out of the observer's field of view than do shiny fibers. I happen to be one of the few blessed people who has actually had my hands on the Shroud with gloves. Unfortunately, Ray will probably frown at me. They were cotton gloves. They were gloves people use to handle photographic negatives and things. But the linen is amazing. It's quite supple. It's where the image isn't, it's got this sheen to it. It looks like a brand new linen that's been yellowed. I mean, that old, and that's still what it is. So at any rate, this is the idea I had while I didn't have this idea. The thing bothered me that this happened. I wondered why. After we returned from Turin, I put it on the shelf of my mental library. I was going to pull it down and think about what might be the cause of this effect. Like so many such ideas, it faded from memory. Until Joe Marina asked me if I would like to give a presentation at this meeting. And after first declining, this memory popped, this 30-year-old memory popped back into my mind. And I said, you know, this might be worth exploring. So I told Joe that I'd do something. As a laser and optical engineer, I focused on what the optical effects, what the optical basis for this effect might be. And this led me to the hypothesis you see here. And I'll expand on that as I go forward. And this is what I mentioned before. The consequence of this hypothesis, if it's correct, is what I've been talking about. Now here's some of the microscopic photographs taken in the 1978 tests. And you'll notice areas such as here, on top of this there's a little bit of image. On this one there's a little bit of image. But if you look at parts of the fiber like this, parts of the fiber that get down into the weave where they didn't contact the body, you can see that sheen I'm talking about. It's a nice, very noticeable shininess to the individual fibrils. So I set up this experiment. I had a real high-tech laboratory. It was the living room of my apartment. And what I fundamentally did, the first thing I wanted to see is how if I could measure the reflectivity of the cloth as a function of viewing angle, that might tell me. What I was after is how much diffuse light is there compared to the shiny specular reflection. And I'll explain that in a minute. But so what I did is I set this up, and I had a light source through a fiber and a focusing lens so that the spot here was a small diameter, about 2 inches. And I had the same optics here so that only that spot was being focused into this fiber going to the light sensor. And then my cloth, I looked high and low in Albuquerque, and because I kind of did this at the last minute. I looked high and low in Albuquerque. I couldn't find any linen cloth. In particular, any was shiny, and no hope of finding the herringbone weave. But I did find a polyester curtain cloth that had a good sheen on one side and was, to my eye, totally flat on the other side. And I figured, well, if I use the flat side to represent the image area, although this would be the extreme case, and I use the shiny side to represent the pristine cloth, I can at least collect some data and see if there's support for the hypothesis. And I did 3 experiments with this. The first one, I put the light source at 0 degrees, perpendicular to the cloth. And then I moved the receiver from plus 60 to minus 60 degrees, about that. The second experiment, I moved the light over to 60 degrees, and again, took this from minus 60 to plus 60. And then I did a third experiment, which is more like the reality of what you see in the Shroud. I put the light right here at 0 degrees. I took the detector and I backed it up in 2-meter increments from 2 out to 10 meters and recorded the difference. Each place, I moved this cloth to the flat side, the shiny side, the flat side, to the shiny side, and recorded the data on an oscilloscope like this that I could go back later and digitize and read the value. This is right here's the raw data, and you can see clearly that this is the angle here, and this is how much light intensity relative, actually in this case it's both side of the sensor. And you can see that the red line is for the satin side of the cloth that had the sheen to it. The blue is for the flat side of the cloth. And you can see overall that indeed the shiny part was reflecting more light, as you might expect. And then what I did was I normalized both of them to their peak values to see what the peak to valley difference was in the 2 of them. And again, and I'm doing this not having a clue what this data is going to mean to me. I just took the data, which is a good way to be objective. And so over here, I can see the peak to valley on the flat cloth is greater than the peak to valley on the cloth with a sheen. And you can see, as you would expect, the back reflection from 0 degrees, the angle that the light was at, is the greatest because you're getting a little bit of it as a mirror-like specular reflection. The next slide shows the data from when I put the light at plus 60 degrees, and you can see here the data peaks at minus 60 degrees. A mirror, light comes in, goes back out at exactly the same angle, so you would expect that. And here I've normalized the 2. And now you see at this angle, the flat cloth has, yeah, I see this angle, the flat cloth has less peak to valley than the shiny cloth. So again, boy, I've got data, what the heck does this mean? And these are the results of the backing off the detector 2 meters at a time, as if you're backing away from the Shroud. And again, you see more light from the shiny cloth, less from the flat cloth. But when I normalize them, the shiny cloth, the light from the shiny cloth, decreases faster than the light from the flat cloth. Totally contrary to my hypothesis. All right. Next question is, all right, I got this data. What's it telling me? Is there any way I can use this data to make some conclusions about the specular versus diffuse reflection? This diagram here shows a light illuminating the surface of a small spot, a light receiver represented by an eye here, and there's a specular mirror light component that goes off in the negative angle from where the light is, and then there's a diffuse component for those technical folks, a Lambertian reflection, that covers 180 degrees and indeed is the same intensity no matter what angle you look at it from, and it's only a function of the angle the light comes in from. And so This is kind of the geometry of what happened. And so what you would see in light, if you put a light detector, you would see a certain level of light here, much brighter light here, and then the same level over here. So the received intensity is the ambient light, which is the room light. I turn the lights out and they're in the dark. So that goes to 0. Plus the diffuse component plus the speculative component. Well, I did quite a bit of searching on the web, and I found an empirical model called the Phong model that was developed early on in computer and film graphics to make graphic objects look realistic in terms of the lighting. And basically the equation here is what I just showed you. The received intensity is the ambient intensity plus the diffuse intensity plus the speculative intensity. Ambient was 0. The term for the diffuse intensity is a coefficient I'll talk about in a second. The amount of the incoming light, the intensity of that, times the cosine of the angle the light comes in from. And again, it's when you look at it, no matter where the receiver is, it sees the same number. The specular light is a little different. It's got its coefficient times the intensity of the incoming light times the cosine of an angle beta, which is the difference between the specular reflective angle and the viewing angle here. Raised to an arbitrary power n. And again, this is an empirical model. You make it and you play with it until you like what you see on the screen, until it looks realistic. And so you put all these in an equation. And this is what you see here, this equation. The case of D and case of S are coefficients on the specular and diffuse components ranging from 0 to 1 that determine the relative brightness of the two of them. And of course, n is what they call the shininess exponent. And as an example, here are some balls. N is the shininess exponent. A high n means there's a small spot of shininess. That little peak that pops up is quite narrow. As you get down to low values of n, like 1, the shininess is a much larger, almost diffuse light itself. In terms of the reflectivity coefficients, kind of the measure of merit here is the ratio of the two. And you see if the specular, in this case, is twice the diffuse, you get a lot of light here and almost dark back here. And as you go down in that ratio, you pick up more and more of the background diffuse, where this one's almost totally diffuse here, because of the ratios. All right, so what I did was take that normalized data, the red and blue curve you saw before, and I wrote a version of the Phong model on Microsoft Excel, and I tinkered with the coefficients and the power until I got a good match over the central part of my data. Notice that in both cases, I break from the Phong model out here at this plus and minus 60 degrees. That's getting to be a fairly glancing blow off the cloth. And for some reason, the model breaks down there. In truth, modeling cloth reflections is a very complex thing to do. I've chosen the simplistic model just to see if I can get enough information to support my hypothesis. And so this may be due from what I've read. That may be due to structure in the cloth itself, adding yet another component to the Phong model that I haven't considered. And these are the relative values of the coefficients and the exponent for the two. Now I'll conclude these, I'll interpret these in a minute. And then here again we fit the Phong model to the experiment 2 where the light came in at 60 degrees. And again you see the break from the Phong model as you move away from the peak. All right, what does this mean? The ratio of the specular to diffuse coefficients for the satin cloth and the flat cloth has a higher coefficient than the satin cloth, which is contrary to the hypothesis, because this says that the flat cloths has relatively more specular than diffuse. Should be the other way around. The ratio of the two shininess exponents, however, here you see the satin is larger than the flat, which is as you would expect when you have a larger specular component. The other thing I looked at then, if you remember that little blip sticking up from the diffuse, it had an angle to it. And so I took that angle, the full width half max of that angle, and compared it for the two cases. And again, you would expect the flat cloth to have a larger angle than the satin cloth. Well, guess what? They're both the same. So let's look at some conclusions. Based on the analytical and experimental results, the hypothesis has not been demonstrated. Two possible explanations. The experiments did not accurately represent the shroud conditions. That's an absolute fact. I didn't have anywhere near the kind of cloth, anywhere near the kind of lighting, and so that's definitely true. And then the other very possible thing is the hypothesis is incorrect, and some other explanation for this effect must be found. Now, if any of you are interested in the presentation, or in particular the Phong model in Excel, email me at this address. I'd be glad to send it. I'll leave that up for a second. And so the bottom line here is, what does this all mean? Well, one of the reasons I did it was to stimulate some thinking. Somebody out there may say, oh, I have an idea. And hopefully maybe one of the young third wave folks will come along and say, yeah, I'm gonna spend some more time on this. But in terms of what I came to conclusion I came to when I asked myself, what does it all mean, is represented by the next slide. Now, I'd like to take just a couple minutes to talk about another subject that, again, Rex's talk last night kicked another memory out of my recesses of my mental library, and I think it's quite important. And so I'll just go over a couple of slides with this. In 1980, I was exploring alternative answers for the three-dimensionality. What could be causing this? And I gave it quite a bit of thought, and it occurred to me that maybe the highest points have been in contact with the cloth the longest period of time. Therefore, more of whatever causes the image, the body exudations, have more time to cover the fibers and seep along them and into them by capillary action. And so, of course, that raises the question, why would the cloth be in contact with the high points, the dark points, longer? Well, an answer to that is, maybe the cloth slowly sagged into the lower parts of the body over time due to the absorption of moisture given off by the body. Well, I thought, hey, this is pretty good. I can do this, and I can test this. And so, yeah, I set up this experiment. I made a plaster negative mold of my face. And for any of you young folks, you want to repeat this, put Vaseline on your eyebrows first. This is a lesson learned here, all right? I put the face into the bathtub, covered it with a linen cloth, nowhere near the shroud kind of cloth. It was actually a linen napkin from my grandmother's old linen stuff. But it was fairly heavyweight. I put a humidifier in the bathtub, and then I taped clear plastic over it, turned the humidifier on, and every hour I went in and recorded my visual observations of what it seemed to do. And sure enough, initially the linen only touched the highest parts, the chin, the lips, the nose, the eyebrows. And over the next 12 hours, and that's how long it took it in this experiment, didn't measure the humidity, crude experiment, but nevertheless, after 12 hours, the cloth progressively sagged into these other areas, on into the crease of the lips, and the only thing it didn't touch was the very small recesses where the cloth just couldn't get down in there. And so, you know, this since this experiment seemed to demonstrate a very simple physics-based explanation for the three-dimensionality, I talked to a few of the folks at the 1980